In this tutorial, we will be discussing the pH of weak acids and bases. Okay, just as a little review, pH is the negative log of H3O plus. In a neutral solution, H3O and OH minus are equivalent at 1 times 10 to the negative 7. This would make the pH equal to 7 for water at room temperature. The normal range is from 0 to 14. However, pH can be negative, meaning it's very acidic, or it could be larger than 14, meaning very alkaline or very basic. pH that's negative is below 7. Here's 7. Anything below is acid. Anything above that is base. 7 itself is neutral. The lower the pH, the more acidic the solution. The higher the pH, the more basic the solution. 1 pH unit corresponds to a factor of 10 in acidity. So the mathematical relationships are, as a summary, pH is negative log of H plus, POH is negative log of OH minus. If you wanted to get rid of the log, you would use 10 to the x to the negative pH or negative POH. You also have the equivalent of H3O times OH minus is equal to 1 times 10 to the negative 14 for the equilibrium constant. And then pH plus POH is equal to 14. Now let's do one with a strong base first. CaOH2 is a strong base. When we put it in water, it breaks down to Ca and 2 OHs. So that means if we have 0.001 mole in 1 liter, that's 0.001 molar. That means once it breaks down, we have 0.0010 molar of Ca2 plus, but because of the 2 for OH minus, we're going to multiply that by 2. So it would be 0.0020 molar. So let's calculate the H3O plus and the OH minus. Well, the OH minus we've already calculated right here. The H3O plus, OH minus times H3O plus is equal to 1 times 10 to the negative 14. We're going to plug the 0.002 into the OH minus. And then we're going to divide both sides by 0.002. To have that come out to be 5 times 10 to the negative 12. If I was then trying to go one step further and figure out the pH, I would want to take the log of this. So as a reminder to put that into your calculator, 5 EE negative 12, then push the log button, and then take the opposite of the sign. So it comes out to be negative 11.3. But we change the negative to a positive to be positive 11.3, which because it's above 7, it's basic. Now, a weak acid is a poor hydrogen donor. It has a very small Ka value. The weaker the acid, the stronger the corresponding conjugate base, meaning the conjugate base is a good hydrogen acceptor. As an example, acetic acid is only 0.42% ionized when the acetic acid is 1 molar. That is why it's considered a weak acid. The dissociative acetic acid is as follows, whereas H3O plus and A minus, notice the double direction arrow. The H3O plus is small from the weak acid's dissociation in water. H3O plus is a stronger acid than acetic acid. Therefore, the value of Ka of acetic acid is very small. As a base, the acetate ion is stronger base than water. Alright, so let's do a few examples of these. Because they're not dissociating all the way, you notice that we keep using the equilibrium constant. Well, this is because we can actually figure out the equilibrium state of these compounds. So for instance, we're dealing with HCN now. So HCN is added to water to produce H3O and Cn minus. Water is liquid, and so it's not included in the equilibrium equation. So we can ignore that off the bat. We have 0.100 molar to begin with. So initially, we have 0.1 molar of the HCN, 0 of the H3O, and 0 of the Cn. As it disassociates the change, we're going to be minusing X plus X plus X. So the equilibrium state will be 0.100 minus X, then X and X. That comes out to be X squared over 0.100 minus X is equal to the equilibrium constant of 4.9 times 10 to the negative 10. That's given to you in the question right here. Now, we're going to assume that since this is a weak acid, in other words, the Ka is much smaller than 1, that this X here is negligible. We're going to assume that's insignificant. So we're going to subtract it out. And we're going to solve for the X's on the top. So we're assuming this is insignificant. And we're going to actually double check that at the very end. The first thing I want to do is get rid of the 0.1, so I'm going to multiply it across. That comes out to be X squared is equal to 4.9 times 10 to the negative 11. To get rid of that squared, I'm going to take the square root on both sides. That gives me X is then equal to 7 times 10 to the negative 6. I want to double check my assumption here. If it's within 5% of the original concentration, we're okay. So 7.0 times 10 to the negative 6 divided by the original concentration of 0.100 times 100. That comes out to be 0.007%. So since it's under 5%, we can assume that that assumption was fine, and we can just move on. We don't have to go back and do the quadratic equation. Now I want to take a minute to also talk about this in another way. That's also called the percent ionization, and we're going to discuss that at the very end of this tutorial. The percent ionization is the amount of ionization that occurred with that initial compound. And it's another way to determine the strength of the acid or the base. Let's try another one. We have HNO2 now. We're putting it in water. Double-sided arrow because we're looking for equilibrium. We're starting off with 0.2. We're ignoring water because it's a liquid. We initially have no H3O or NO2. There's a little bit there from the water, but it's such a small amount that it doesn't matter. The change is x. So that means that's 0.200 minus x. So that gives us x squared So x squared is over 0.200x minus 0.200 minus x is equal to 4.6 times 10 to the negative 4. Once again, we're going to assume that that second x on the bottom is not relevant. So we're going to cross multiply first, and that comes out to be x squared is equal to 9.2 times 10 to the negative 5. To get rid of the square, we're going to take the square root of both. And that comes out to be 0.00959. Let's double check our assumption. 0.00959 over the initial concentration of 0.2 times 100. That comes out to be 4.8%, which means it's under the 5%, but just barely. And that's also the percent ionization. It's asking for the pH as well. In order to get the pH, we had to solve for the H3O first. So to get the pH equals to negative log of our H concentration, which is 0.00959. So the pH is then equal to 2.02. So let's say it doesn't work, that the approximation works out well. So let's try worst case scenario. So we have HClO2. 0.100 is what we're starting with. H2O goes away, 0 and 0. We're losing X and we're gaining X on this side because it's breaking down. Our equilibrium constant's right there, 0.011. All right, we're going to first of all assume that that x is insignificant, so we're going to get rid of it. Then we're going to cross multiply. That comes out to be x squared is equal to 0.0011. To get rid of that square, we're going to take the square root of both sides. And that comes out to be 0.033. Now let's see if that's within our 5% rule. 0.033 divided by 0.100 times 100. That comes out to be 33%. We are way off of our 5% max. That means that we have to go back and do the quadratic equation. We're going to start with the same numbers. I'm not going to redo everything. So, we said that we have x squared over 0.100 minus x is equal to 0.011. That was from the previous slide. First thing we need to do is cross multiply. All right, now we're going to distribute. And we're going to rearrange the equation to solve for 0. So in our quadratic equation, this will be our A, this will be our B, this will be our C. If you've forgotten what the quadratic equation is negative B plus or minus B squared minus 4AC over 2A. So our negative B would be negative 0.011 plus or minus B squared, which is 0.00121, 3 zeros, minus 4AC, which is 4 times 1 times negative 0.0011, which comes out to be negative 0.0044. All over 2A, which would be 2 times 1, which is 2. Which means when we solve for this, we're going to have two different answers. 0.028 or negative 0.039. Because of that negative sign, we're automatically going to discount that one. 0.028 is the final answer. So let's talk about the weak bases. So we want to calculate the pH for 0.01 molar NH3. We cannot calculate pH from the solution directly because this is a base. That gives us the information for OH, not H. If we know the POH, however, we can compute the pH from the relationship of pH plus POH is equal to 14. So we can start it with the ice. From here, we can say that we are starting with 0.01, nothing for the water, then 0 and 0, minus x plus x plus x, so that's 0.0100 minus x, x and x. So x squared is equal to 0.0100 minus x is equal to the equilibrium constant of 1.80 times 10 to the negative 5. I'm going to try to assume that this bottom x goes away because it's not big enough. So therefore, we're going to go ahead and cross multiply, and that comes out to be x squared is equal to 1.80 times 10 to the negative 7. Take the square root of both sides. X comes out to be 4.24 times 10 to the negative 4. That gives us our x here and our x here, which means we now know the OH minus concentration. Let's double check that we were able to discount that x. So we're going to figure out the percent ionization. So 4.24, I'm going to start at the top, times 10 to the negative 4 over our initial concentration of 0.01 times 100. And that comes out to be 4.24%. So it's okay. Barely making it, but it's okay. Alright, so now we have the OH minus concentration. From here, we know this is our OH minus. We can figure out the H3O plus. You can either figure out the H3O plus and then find the pH, or you can figure out the POH and subtract it out. So I'm going to go the route of solving for H3O plus. So H3O plus times 4.24 is going to equal 1 times 10 to the negative 14. We're going to divide both sides by the 4.24 times 10 to the negative 4. That comes out to be 2.36 times 10 to the negative 11. If I take the log of this number, the negative log, we find out that the pH is 10.6. Okay, as I said before, another way to measure the strength of the acid is to determine the percentage of the acid molecules that ionize when dissolved in water. This is called the percent ionization. The higher the percent ionization, the stronger the acid. So it's the molarity of the ionized acid, which is the X that we keep solving for, divided by the initial molarity of the acid times 100. So it's the exact same steps that we were doing when we were solving for when we were checking the 5% rule. And so here we go. If we went here to any one of these, or we checked here for instance, times 100%, the 4.8%, that's your percent ionization. Alright, and that is how to solve for pH given a weak acid.